really healthy environment. So he looked back at his notes and was like, what was that formulation? And so over many years it was isolated down to about 13 species, but they're all what's generally recognized as safe according to the FDA because they are the same sort of things we'll find in yogurt, we'll find in culturing miso, or we'll find in beer brewing, any number of things. And so there's been one organization called the Asia Pacific Natural Agriculture Network that is one of the few organizations that I was inspired by to try to create my own little place in the world. So I've been very influenced by the effective microorganism technology of Japan, but then this is where what I've been doing out in the field out here also is a blend between Japanese natural farming and Korean natural farming. And the backbone of Korean natural farming they call the IMOs, or indigenous microorganisms. And so that whole idea is a commonly repeated statistic is you get 50,000 microbe species in 1 teaspoon of soil. So a lot of those species of microbes can't be cultured on a petri dish. For instance, mycorrhizae I spoke about in the last talk, those can only be cultured on the root of a species that, lots of species will have their own mycorrhizae. Some plants like brassica have no fungal relationships at all. But the idea being that, you can try to self-similarly propagate microbes from the forest and then spread them into a forest environment, from the forest environment into a field and orchard setting. So it's kind of like, the way I like to think of it is either like a shotgun approach or like an all-you-can-eat buffet. So if there's 50,000 species in 1 teaspoon of soil, there's going to be a lot of nutrient cyclers. Some are going to specifically be like solubilizing phosphates, like the mycorrhizae. You're going to have nitrogen fixers, what have you. And so the idea is that we're going to find symbiotes even though we don't know what they are or necessarily what they're doing. We're presenting the roots of the next thing that we're transplanting them to, that there's going to be just this whole diversity of species that enables self-selection, because then you get this whole feedback loop between the soil and the microbiome at the roots, because up to 40% of all the photosynthesis, a tree that is not being given chemical fertilizer, 40% of its photosynthesis will go down into the roots to feed the microbes through what's called root exudates, which is basically like liquid sugars. And so if you were to, say, take a sample of the microbes at the base of a tree, it's going to be different all throughout the season, because the plant, like we know, it's going to want more potassium as it's starting to fruit, a little more phosphorus, it's going to want more nitrogen in the spring. So it's been described as like a language between the trees and the microbes. The exudates change to attract things throughout the year. So if they're needing more, phosphorus, they'll tailor their sugar into the soil to attract then more fungi. And so the idea is, I guess I've been working with is that, the gut and the microbe relationships, it's like probiotics for the soil basically is one of the simplest explanations. I'm trying to work with like wild harvesting probiotics, symbiotic sort of microbes, and give them to trees, either at the beginning of their life so that they're going to start out full of vitality, or I've worked a little bit here in this garden where I have, for 2 years, a row of trees now has been given indigenous microorganism cultures that I've done both a sort of solid state fermentation, what's called bokashi in Japan, or there's 3-4 stages of IMO cultivation, according to Master Cho of South Korea. And so the idea is once you can kind of get a stable microculture from the forest, you can then inoculate it onto a crop residue. For instance, rice bran is very commonly used for the bokashi fermentation process. In this case, I went to Conway Feed, got some wheat mill run. I collected some microbes from underneath the roots of hawthorn and a feral apple tree. And so the idea was that the hawthorn is in the rose family. It's going to attract very similar symbiotes to what is an apple tree, the apple also being in the rose family. But the thing is, if you look at all the native hawthorn trees, you don't ever see any anthracnose. So this is the idea, is that by providing like this diverse all-you-can-eat buffet of root symbiotes, that then you have competitive exclusion of pathogens. So then you see less powdery mildew, or you see less anthracnose, see less insect pressure, because then the plants get a built-in immune system.
So Peter's going to be giving a talk and a walk out in the fruit garden at 1:30 to 2:30, and so if you want to learn more about this, he's got some charts, etc. And so it's a great way to go out and learn more and ask the questions, etc., etc. So I wanted to go through. I wanted to ask Doug. So you don't work so much with perennials,